Hi everyone, welcome back to another video. So we've just now finished combining resistors and we've also done Ohm's law. So we're moving on to basic circuit laws, which are KVL and KCL. If you don't know what KVL and KCL are, we'll cover them now. KVL being Kirchhoff's voltage law and KCL being Kirchhoff's current law. So let's go down base. What I'll do as well is, if you want all of these notes that we've done so far, I'll upload them onto my Dropbox and I'll leave a link in the description. So take a look in the description. Alright, so we're going to cover firstly, so we'll just do basic circuit. That's right, current now. Basic circuit laws. So two of them. So firstly we have, oh, this guy's name right. 2 H's it is, isn't it? Kirchhoffs with 2 S's. Yeah, that's right. Kirchhoffs, yeah. Voltage law. And Kirchoffs. Don't make me write that again. Let's do that. Copy and paste that. Current law. Cool. That's his two laws. So Kirchhoff, I think his name is Gustav. Gustav, I think so. He's a German dude who was in the 1800s, and he came up with these two laws. So yeah, thanks Kirchhoff. So let's start with Kirchhoff's voltage law. It's usually shortened to KVL. So what the law states is that in any closed loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop. So that might seem like a mouthful. In any closed loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop. It's fairly basic. You'll get it. So basically, if you take any path or circuit, right? Take any circuit you want. Start it from one point. For example, start here. Different color. Right, let's imagine you got some components here. Right, any circuit you want. Start from any point you want. Go around that circuit, measuring all of the voltage drops. When you get back to that point, when you add it all up, all of those voltage drops will equal back. And when you get back to that point here, they'll equal 0. Right. Let me draw a better visual representation for you. So do a basic circuit. We've got a voltage source here. Let's give ourselves a resistor here. And give ourselves a resistor here. Okay, so we call this R1, R2, and we call this V. Okay, so what we're saying is that the voltage drops around this loop here are equal to 0. So you take the voltage supplied by V1 minus the voltage drop across R1 minus the voltage drop across R2, and that gives you, when you get back to this point here, 0. And interestingly enough, if you started here, right, you'd go here, you'd get minus R1, you'd have a voltage drop of R1, then you'd get to here, you'd have a voltage drop of R2, you'd come back around to here, now you'd be at like minus, I don't know, 10 volts or something. And then when you reach back to here, you'd have a voltage rise, because obviously the voltage source is supplying voltage of 10 volts. So let's say you go plus 10 volts here, and then that would mean that you're at 0 when you get back to here. And you can literally do that for any point in any loop. So going over the law again, in any closed loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop. Cool. Okay, let's do an example, right? Make it a bit more complicated for you. So we've got R1. I've mentioned before that sometimes I draw resistors with squares, sometimes I do the squiggly. Depends on the day, really. Depends how I'm feeling. All right, and yeah, we can just finish this here. So we've got 3 resistors. We'll give them R1, R2, R3. Right, and then let's go. We'll call this voltage source E. So sometimes we refer to them as E, sometimes we refer to them as V. Usually when you're dealing with Kirchhoff's voltage law, it kind of makes sense to go with E, which you'll see in a minute. All right, so what we do is we usually write what we call is a KVL equation. It's called that because obviously it's Kirchhoff's voltage law, and we're writing an equation for it. So we know that the loop, this loop here, start from here, go all the way around, right? That whole loop is going to be equal to 0. We know that, right? So what we can say is we can take the voltage drop, let's say of E, right? And then we can minus the voltage drop across R1, which would be V1. And we could minus the voltage drop across R2, which would be V2. And we can minus the voltage drop across R3, which would be V3. And that, all of that is going to be equal to 0. And this here is our KVL equation. Cool. And if I asked you, for example, how do we work out what's the value of E here? And we know that E, for example, you could do some algebra here. If you added V1 plus V2 and V3 to both sides of this equation here, if you added it to both sides, what would you get? You'd get E is equal to V1 plus V2 plus V3, which is obviously the case because, as we've said, you go around a whole closed loop. So if we take some examples, if we said that, for example, E was 25 volts, and we said that the voltage drop across R1 was 10 volts, R2 was 10 volts, then R3, the voltage drop would have to be what? 5 volts, right? So you can see here that E is going to be equal to the voltage drop across all the other components in that loop, providing obviously there aren't other voltage sources. Cool? Okay. Let's do, I think, should we do another one? Okay, let's do another one. So we'll do a basic one. Yeah, so this is another way of drawing a voltage source. But we'll do a basic one now. We've got 3 resistors again. So the voltage drop across this resistor is 5 volts. The voltage drop across this resistor is 3.5 volts. And the voltage drop across this resistor is 1 volt. What's the value of E? Well, E is just equal to 5 volts plus 3.5 volts, 1 volt. So E is equal to 9.5 volts, right? So just, I mean, if you've done this before, this should just be fairly basic, and hopefully I'm just reminding you. If you're still struggling with that, then just practice. Practice makes perfect, as they say. All right. So let's do what happens when we have 2 voltage sources and are a bit backwards. Okay. So let's do 1 voltage source here. Pick a resistor here. Another resistor here. Then let's put there you go, voltage source like this. As you can see, for these voltage sources, you've got positive, negative, right? Then you're gonna have positive, negative here. So these 2 voltage sources are reversed; they're backwards from each other, right? So here now, determining how we're gonna figure this out can be a little bit complicated, and this is where using the KVL is really helpful. So if you remember the KVL equation, right? What we can do is we can start at any point. For example, we'll start here. Doesn't really matter where you start. Go around the whole thing and go back to that starting point, and that's going to be equal to 0, right? So what we'll do is let's label these label the resistors. We'll label this one E1 and this one E2. Alright, so one thing I forgot to do is I forgot to label the resistors. Now, when we're dealing with labeling passive components, it doesn't really matter which way you label it, really. Because when you're working out in your equations, you end up with either a positive or a negative sign, or either the current or the voltage, and that's how you know that it just needs to be in a reverse order. So it's not too much of a problem. But what we'll do is let's just label this one negative, this one positive, this one positive, this one negative. Doesn't really matter. Alright, so now that we've got them all labeled, one thing I just want to mention is that when it comes to, for example, when we start off here at our point of the KVL, when we reach the negative sign of the voltage source, what we're saying is that here, this point here, has a lower voltage than this point here. Here has a higher voltage point. Why? Because now we've introduced this voltage source to the loop, and then we're having a voltage rise across E1 of whatever the value of E1 is. So that means that when we're writing our KVL, we're going to have plus E1. Then we go back around to here, we're reaching the negative sign. So basically, based upon this, we're going to continue our convention. Again, you might see some people online that will do it the opposite way. Again, it doesn't matter, as long as you remain consistent in your labeling of the node. So since we've reached the negative sign here, and we're having a voltage rise across E1, we've reached the negative sign here of R1. So that means we're going to have a voltage rise again of R1. And that might sound weird if that's the first time you're hearing that, a voltage rise across a resistor, but don't worry about it. And then we're reaching the plus sign here. So remember, we're having, generally speaking here, we're having a voltage rise at negative. So that means here we're going to have a voltage drop. So we're going to have a minus. And here again, we're going to have a voltage drop. So we're going to have a minus. So when we write our KVL, we're going to have plus E1 and then plus V1, which is the voltage at R1, minus V2, and then minus E2. And all of that is going to be equal to 0. So you could rearrange that. You can add V2 and E2 onto each side, and that will give you E1 plus V1 is equal to E2 plus V2. And both of these are obviously correct. And this is our KVL for this equation. Cool. Okay, so there is I could go a lot deeper and we could start solving some equations and I could chuck some numbers in here, but we're going to do that a lot when we cover nodal analysis and mesh analysis in the next couple of videos. So I'm not going to go too deep into this here. I'm going to stop here and we're going to go into KCL, which is Kirchhoff's current law. So if you do feel like, you know what, there's a lot more I could go into, again, you're more than welcome to jump online and practice a whole bunch of questions. So let's move on to KCL. So again, Kirchhoff's current law. Let's go with the official definition. First of all, that's a D, by the way. D. Official definition is total current or charge. I just memorized it as total current, but yeah. Total current or charge entering a junction. We'll go over what a junction is in a minute. Or node, same with node, is exactly equal to the charge leaving the node as it has no other place to go except leave. And why? Because no charge is lost within a node. So if you just started studying electricity, the easiest way to look at it is just think about water and pipes. That's what I do and it works nicely for me. So let's just go over this definition again. Total current or charge entering a junction or node is exactly equal to the charge leaving the node. So imagine you had, imagine we had a mountain and you had a tunnel there, right? You had a dark tunnel, and you know you had 10 cars. Imagine it's just 10 cars entering into that tunnel. We're saying that however many cars enter the tunnel, then they're going to exit that tunnel, and no cars are going to remain inside the tunnel. Yeah. So what we're saying here is that however much current enters a node or a junction, then that same amount of current is going to leave that junction. Okay, so the way that I visually like to look at it is, this will be a node. If you imagine like nodes, like neural networks, if you know what they look like, you'd have like, for example, another node here, and then that would break off into like 4 nodes. You'd have a node here. Nodes are kind of like, yeah, like that, right? So let's just simplify this. Okay, so that's the node. Yeah. So what we're saying is that however much current enters the node. So imagine here we had a current I1 and we had a current I2 entering the node. Then what we're saying is that if you had these two currents, I3 and I4, entering the node, I1 and I2 would equal I3 and I4. So I look at it in terms of water. If you had 50 liters of water flowing in here and 50 liters of water flowing in here, then you would get not necessarily 50 coming out of here and 50 coming out of here. That wouldn't necessarily be the case. But in total, between the two of these, you would have 100 liters of water coming out of. Right? So we're saying that what goes in must come out. Right? Similar kind of like to what goes up, what must come down. However much current goes into a node, then that amount of current is going to exit the node. Okay, let's do some examples because it'll make way more sense when we actually use electricity. So let's say we had a node here, and a node here. So imagine we had, so we had 5 amps of current. So remember, with KCL, with Kirchhoff's current law, we're dealing with current, right? No longer voltage. So we're talking about current flowing into a node. We've got 5 amps of current flowing in there. And let's say we've got 7 amps of current flowing in there. Then here into this one, is it possible, for example, that we could have 2 amps of current going into it? It's not possible. Why? Because then you'd be having 14 amps of current going into this node with nowhere for it to go, which isn't possible, right? So that means that guaranteed, this node here, or this point here, you're going to be having how much? 12 amps of current exiting. So we're saying if we have 5 amps coming in here and 7 amps coming in here, then we're going to have 12 amps coming out of there. Let's see if you can work out this one. Let's do another one. If we have that, right, and then let's do another one. And yeah, let's go like that. And then what we'll say is, let's say we've got 2 amps coming out of there. Let's say we've got 7 amps going in there. And then we've got let's say, okay, we'll say we've got, let's say we've got 1 amp going in there. Then what is the case for here? Let's say we had I1. What is the value of I1? Right, so think about it. So we've got 7 amps of current coming into here, and we've got 2 amps leaving there. That means that here we've got 5 amps, right? Yep. And then so we've got 5 amps still coming this way, and we've got 1 amp coming down into here, which means that we must have 6 amps of current going out of there. So this is basically KCL for you, and you'll get it when we're dealing with more circuits. Let me do maybe a more simpler one. We've got one big node here. Let's do 1, let's do 2, 3, 4. Then let's do 5. Okay. So we got current coming in, current coming in, current coming in, and let's do current coming in, current going out. So if we've got 1 amp here, 3 amps here, 1 amp here, 1.5 amps here. Then what's the value of this here? Let's call it I1. What's the value of I1? You simply just add up all the other nodes, right? And then you get the value of I1. So you've got 3, 5, 6.5. So I1 is equal to 6.5 amps. Where you might get possibly confused is when you start to see minuses, right? So let's duplicate all of this. Okay, so what happens if I say here we've got minus 3 amps going into here? What's the value of I1? So this might throw you off a bit, but think about it. If you've got minus 3 amps coming into here that way, what that tells you is that you've actually got 3 amps going that way. That's it. So if you instead take it to mean 3 amps that way, then that tells you that you've got 3 amps out, 3 amps in, which is equal to 0. So these two cancel each other out. Then you've got 1 amp plus 1.5 amps, 1 amp plus 1.5 amps, that gives you 2.5 amps. And so here, I1 must be equal to 2.5 amps. And that's it. Okay, so just the same as we was able to write KVL equations for our KVL up here, just the same way we was writing KVL equations. Similarly for nodes and stuff, we write Kcl equations. So let's put Kcl equation. Okay, so imagine we've got a node. Let's do another node. Make it bigger. Okay, we've got current coming in. I could probably draw that better. And then let's go current coming in, current exiting, and current exiting. So I'm not going to give them actual values. I'm just going to give them labels now. So let's go I1, I2, I3, I4, I5. So what we're saying here is that what the Kcl law tells us is that the algebraic sum of all of these currents is going to be equal to 0. So we can start writing our Kcl equation by saying that all of these are going to be equal to 0. And then we can just write them on the basis of how they interact with that node. So which ones are entering the node, they're going to be, positive into the node, and which ones are exiting, they're going to be negative, subtracting from the node. So we can just say plus I1 plus I2 plus I3 minus I4 minus I5 is equal to 0. And this would be our Kcl equation. And then obviously we could reword that by saying I1 plus I2 plus I3 is equal to I4 plus I5, because we just add I4 and I5 to both sides. Cool. And so this is if you can understand this Kcl and the previous part KVL equations, then when we're going to move on to nodal analysis in the next video, and that's going to be a whole bunch of these Kcl equations. And then we're going to move on to mesh analysis, and that's going to be a whole bunch of KVL equations. So as long as you can understand the concept, in the next video, you'll see us do a lot more problems and stuff, and it will start to make a lot more sense. Cool. Alright guys, thanks for watching, and I'll see you in the next one. Peace.